Hello, my dear students. I welcome you all once again to our online lecture series. In today's video, I'll be talking about the classification of differential equations. All right, let's delve deeper into the video.
Welcome to this video on the classification of differential equations. This material is delivered by Dr. Shubham Manimohan Singh. A differential equation involves a function and its derivatives, modeling how quantities change over time in fields like economics. Classification is vital as it guides you to the correct solution method for your problem. In economics, differential equations model growth, decay, and adjustment processes. The first classification is between ordinary differential equations, or ODEs, and partial differential equations, or PDEs. ODEs have derivatives with respect to only one independent variable. PDEs use partial derivatives with respect to multiple independent variables. In introductory economics, we mainly focus on ODEs. Next, we classify by order, which is the highest derivative present in the equation. First-order equations contain only the first derivative, like y prime. Second-order equations contain the second derivative, like y double prime. Higher-order equations are less common in basic economic applications. Linearity is another key classification. A differential equation is linear if the dependent variable and its derivatives appear only to the first power and are not multiplied together. Linear equations are much simpler to solve than nonlinear ones. An equation is nonlinear if the dependent variable appears to a power other than 1. Linear differential equations are also classified as homogeneous or non-homogeneous. A homogeneous equation has a right-hand side equal to 0. A non-homogeneous equation has a non-zero function on the right-hand side, often representing an external force or input. Homogeneous equations generally have simpler solution methods. Autonomous systems are time-independent,
Meaning the independent variable t does not appear explicitly in the equation.
Non-autonomous systems, conversely, have explicit t-terms. Autonomous equations are valuable in economics for long-term forecasting because they often reach a stable equilibrium. The exponential growth model, dy dt equals k times y, is a common economic application. Its classification is ODE, first order, linear, homogeneous, and autonomous. The solution shows continuous exponential growth or decay determined by the initial conditions. Newton's law of cooling, which models partial adjustment, is dy/dt equals k times a minus y. It is classified as ODE, first order, linear, non-homogeneous, and autonomous. The variable y adjusts toward the target equilibrium A in the long run. Let's classify a practice problem. X prime plus t times x equals t squared. This is an ODE, first order, and linear. Since the right side is t squared and not 0, it is non-homogeneous. Since t appears explicitly, it is non-autonomous. Another problem is the capital stock equation. dk dt equals I minus delta k. This is classified as ODE, first order, linear, non-homogeneous, and autonomous. It represents capital change based on investment and depreciation, reaching equilibrium when investment equals depreciation. In summary, always classify a differential equation in the order of ODE or PDE, then order, linearity, homogeneity, and autonomy. This classification determines the solution method. Linear and autonomous equations are often easier to solve and are useful for long-term economic forecasting. Thank you for watching this video on the classification of differential equations.